So today we have 4 presentations in person and 1 virtual one. So we're gonna start, before I Charles Lin, and the title of his presentation concerns decision-making impact on climate net zero challenge. And then, yeah, we can use that.
Thank you, Julie. My name is Charles Lin, and this talk is a little bit different than today. And I have accepted no external funding for this work. Let's start with Alicia Paul. 3 questions. First question, are you worried about climate change? Let me know that they are worried or very worried. Second question, have you made changes in your personal life? And that drops to 6 out of 10, with only 1 out of 10 saying they have made big changes. So presumably the other 5 made small changes. Third question, if you had to pay for it, what would you do? The numbers drop down to 4 out of 10. So there's a gap between expressing concern and action. 7 out of 10 drops to 6 out of 10 in terms of making changes, and that further drops to 4 out of 10 if it costs you something. And this is what I call winning class minds, trying to narrow it. Science is good at winning facts and figures, spreadsheets, megatons, gigajoules. Public doesn't care about that. As soon as you mention tons, you lost people. That's winning the heart. Winning the heart by telling stories, narratives that relate to their values and to the culture and beliefs. And this is my story. Now, I'm going to relate an anecdote. We have 3 children. One of them is a lawyer in Vancouver. And at the time, the Trans Mountain pipeline was a big issue between Alberta and BC. Alberta wanted the pipeline to ship oil from the oil sands to Vancouver and then to Asia. And this was an election issue. This is 2018-19, around that. And I asked my daughter, who lives in Vancouver, she's a lawyer, well informed, Jennifer, are you aware of this pipeline debate? Do you know much about it? No, not really. There's an election debate that's going to affect Vancouver because of the few small bill and so on. Shouldn't you be interested? The response, the reason why I'm not interested, Dad, is because nobody has explained this to me in simple words. Nobody has explained this to me in a simple way. So that's the impetus of me going into an outreach on the kind of issues, the kind of science that is behind the issues that the public is concerned about. Now, we started with pushing into communication experts always say that that's not enough to win the battle. We have to engage. And that's my story. Engaging at the community level. Now, there's a lot of text here. Just focus on the red text. We have decided to use the theme of food waste. Everybody understands that we all waste food, and we don't have to explain what food waste is. And another issue, this is work over the last 6 months, the prevention of federal elections that we went through election. And the community groups were engaged in the past 12 months. Again, the names don't really matter. They are community groups at different levels of granularity, including the largest food rescue organization in Canada, Second Harvest. Pick up food from the farm level, at the supermarket level, and bring it to those who need them, food bags. That's a big operation. We'll see if we can talk about that later. And we work with Seneca College, where we reach youths, and we also participate in a Midtown Toronto area, Eglinton Morris, a group of concerned citizens came together to work on the elections. So, that just finished. So we work with these groups. The key is at the community where the issues affect the community, and we agree to work to start with food waste. So this took place about a year ago. We had reps from 7 resident associations and met with the city councilor. That's George Campbell with the face in that square, me on the upper left, and reps from 7 resident associations talk about urban heat islands. These towers that are putting up within 200 meters of my building, Williston floor tower, 200, 500 meters of where I am. There are 3 towers going up, each over 50 stories high. So urban heat island was an issue that we started with, and then we moved on to household food waste. And this is an explaining article that I wrote, and the numbers are staggering. Every day we waste this. Every day. Staggering numbers. And of course, this security issues on now with the chapters and things work. So we have a member of our group testing different apps that people can use to reduce food waste. This is from the City of Toronto, which addresses waste in general. And this is from our Instagram post. And it's also available on our blog. So it's called Waste Wizard, and it helps you sort different kinds of waste and collection schedules and so on. Apps that people can use, and we tested them and put them on Instagram. Firstly, is targeted food. You can log your food purchase, you can scan the expiration date, right? And then reminders and alerts are set so that you can reduce food waste. Again, from Instagram. And then we organize 2 events. On the left is Second Harvest. You can see one of the events there. Second Harvest is the largest food rescue organization in Canada. They have a fleet of trucks, about 17 trucks. We recently visited their facilities, refrigerated warehouses, and freezers to store food, and drivers to bring the food from the fetch, to get the food from farms and bring them to food banks. So this is the speaker, Mike Clayton, the son of Jack Clayton, the NDP fame, Orange Wave and Quebec fame, and he was a city councillor and now is an executive at Second Harvest. So we organized with different community organizations a talk at the local community center on food waste, and then he participated again with head of sustainability at Seneca, as well as a faculty and youth member who actually tested these acts. Another organization, and this is a poster that we prepared to prepare for the provincial election. So that gives you an idea of the kind of work we do. Takeaway messages. There are already many citizens groups working on climate and environmental issues. If you want to do something that uses the science and technology that you learn about to benefit policy and communities, seek these groups out. At the community level, there is already infrastructure and issues identified. Seek and engage these groups. You forge relationships, share stories, and you build trust. It's about people, all about people. It takes time and effort. People to listen to you takes effort. So there's no shortcut, and it takes time and effort. You rally around a common issue that is of interest to the community, in our case, food waste and elections. And you engage, and then we also engage politicians. I have met with my MPP, we have met city councilors, as I've shown. We're trying to arrange a meeting with a newly elected to talk about climate action. Use the network of networks approach. Resident associations, they have a very well functioning network in many communities. So you don't reinvent the wheel to get people, to reach people. You use those networks in our case. And for this, we reach the community colleges and universities. So that's where we're getting down. And storytelling. You tell stories. You don't talk about spreadsheets, you don't talk about facts, you don't talk about concentration of CO2 reaching 420 ppm. You only talk about that in conferences like this. But when you talk about tons and megatons, you've lost people. So storytelling, I think, is crucial. And I will close with another personal anecdote. Last fall, I gave a talk. I have an affiliation with Harvard University. I gave a talk at Harvard Club of Quebec along the lines of what I just talked about here, but it was a longer version. And then the talk was a young lady. She listened to my talk, and then she came to me at the end and said, that was very interesting. When I heard the talk about climate, I thought it was going to be another one of these doomsday scenario talk. Situation dire, we have a small time window to act, and we can still do it if we act now. The talk was totally different. It was more like what I'm saying, what I'm talking about here. And she said, that was different. And then I said, well, if you want to follow up, yeah. She did. And a couple of months later, I talked to a group of 6 of her friends. And then a few months later, we reached out again. She said, Charles, based on your talk, I started a conversation club. And you were the first one to talk to my friends on this conversation club. On Instagram, I reached them, I advertised your talk, 7 showed up, and your message resonated. Now she's working with our organization. I asked her to develop this idea with us on the idea of a conversation among youth. She's 20-something. So storytelling, personal relationships. If you want to bring hearts and minds, that's the way to do it. And this process for this young lady took 6 months. 1 email at a time, 1 chat at a time, and 1 meeting at a time. It works. It may not work as fast as you like, but don't let anyone tell you what you do won't make a difference. What you do makes a difference. It may not be as fast as you want or as much as you want, but it works. And there is no shortcut. So to forge the relationships, to share stories, and build trust. Announcement to various community groups, and I'm going to fly with my email address, so it doesn't matter. If you want to get in touch with me, you can do so through the conference links, and I'll be happy.
I look at the time, and we don't have time for questions, unfortunately, but we should end early. So please, if you have questions, just come see and chat with Charles. Thank you. This is so true. So our next speaker is Siraj Islam.
I think that was right. It was just because they were hearing him and then also him through that microphone.
That one was muted.
Was it?
See like how that large reservoir, how they're impacted by this reservoir and how the atmospheric and water interaction is happening. So Williston Reservoir, on the slide you can see it's a lake, looks so beautiful. This is an artificial lake or a reservoir which was created by Bennett Dam, which is located in northern British Columbia. It's a very large artificial lake, more than 1,700 kilometer scale area, making it the largest lake in British Columbia and the 7th largest reservoir by volume in the world. The lake fills the basin of Upper Peace River, backing up in the Rocky Mountain Trench, where we have Finlay and Marshall River. So right at the confluence of the Finlay Cosmic River, which ends up making the Peace River. That is where this artificial reservoir is located. And once we have the reservoir, there's a dam which you can see here, and the dam is a dam that is 55 stories high, the 800-meter long dam, which started its operation back in 1968. If we look at pre and post then like changes, land use changes, that's what you can see. This is the map which is showing the Finlay River, Parsnip River, as a confluence here, and then they will make the Peace River. But once we did a dam there and it started its operation in 1968, you can see all that area is now transformed into an artificial. So we have the Parsnip and Peace River there. But this area becomes a Williston Reservoir. As I mentioned, the flooded area by this reservoir is more than 1,700 kilometers. And once that area is flooded, of course, that is the creation of artificial large water body, right? And once we have this kind of large water body sitting there, that is going to impact the local climate. And there are some traditional First Nation communities around this reservoir. For example, the Saeed First Nation is now, they are moved because of this dam creation, they are moved to the northern tip of this particular reservoir. So there are stories where elders from the First Nation, they mentioned that yes, once the dam was created, it was more windier, it is more windier actually. There were changes in temperature, and that is where we have, okay, we said, okay, let's figure this out scientifically in the Western science, and that is where we started by looking at the available observation and trying to investigate, okay, once this new water body is there, how that is going to impact the local air temperature, precipitation, and wind patterns. So that was the driving, that is the objective of this study. We did it in two different ways. I'm just presenting one way here, where we use the reanalysis and some observation and station data. In the second study, which is more published, that is where we use the WF hydro model, and we just created some artificial scenarios of pre-dam and post-dam in the model, and we try to look at the changes in climate. So for this particular study, we used ANA5 and ANA5 blend. Assume many of you know that this is a reanalysis product. It's a blended version of statistical methodologies, real-time stations, and satellite mapping. All that is blended together to create a model-based reanalysis product. This is reservoir, which is shown in blue. What we did is because we want to investigate like the impact of the reservoir in the close vicinity, which we said 10 kilometers around the reservoir. So that black line is showing the 10-kilometer buffer around the reservoir. And trying to cross this 10-kilometer buffer zone climate with this 50-kilometer buffer zone climate, which is shown in the red. So the comparison of the zone which is further away from the reservoir and the zone which is very close to the reservoir, that is showing us because of this water, large water body, how the climate is different than this red circle. So another reason why we did this is because in ANA5 reanalysis, we don't have any pre and post reservoir impact, right? So we need to stick to, for example, we use 1981 2019 data to investigate the changes in local climatic conditions around this reservoir. So I'll be showing you the contrasting results between this red line, and this black line, which will show us like how much the climate is different when we are close to the reservoir and when we are further away from it. So we did that. We created average time series of these two buffer zones, which I'm showing in red and black. And here I'm showing you the different variables that we analyze. For example, this is total evaporation, which is happening in that area. Black color is evaporation happening within the vicinity, and the red one is the evaporation happening outside the vicinity with black and red. which is showing the further away zone from the reservoir. And as expected, we can see that we have, like in summer, we have more evaporation happening. But what we have found is that, of course, once we have this water body, we are seeing more evaporation happening from this lake, especially in the lake summer, from September to November. That is where the lake is evaporating. We confirm that in the analysis. And once that evaporation is happening, that is changing the total air temperature. If you look closely in the black area or in the 10 kilometer zone, the air temperature is increased by roughly 2.5 degrees on average. We also looked at the minimum temperature, which is the difference between maximum and minimum temperature, and we found that especially during the summer and late summer time, there are significant differences diurnal temperature. The diurnal temperature range is reduced now since we have this reservoir. These are the spatial pattern for the sequence analysis. What I'm showing here is the mean average spatial analysis for August to December. Why we are choosing August to December? Because that is where the reservoir is active. It is interacting with atmosphere, heat exchange is happening. So because evaporation is happening. Here, this one is for evaporation, so we can see that more and more evaporation is happening. Our reservoir. This one is the lake evaporation, same as you can see. Transit is also showing us the evaporation increase in late summer or fall. This is air temperature and the diurnal air temperature. As I mentioned before, the air temperature in the vicinity of the reservoir is increased, as well as the diurnal temperature, which is decreased by this large water. We also look at the wind speed changes. Of course, once you have this more than 1,700 kilometer square area, which is filled with water now, that friction and the zero is changing, and that is going to influence the climatology. And what we have seen is that the take-home message from this slide is that yes, wind speed is changing. It's quite variable because it's a complex topography. But in September, or November, December, we can see that that's the wind speed in the back area, which is close to the reservoir. We are seeing that the wind speed is increased. Right? That means that evaporation is happening from the reservoir. That is now changing the wind pattern, and speed is increased. Key finding, if I summarize everything, and I try to, like in my slides, I'm not showing all the technical details because the section is quite different. So that's why I'm just going to my key finding for this study, where what we have seen is we have seen increasing air temperature once we have this, which is around 2.5 to 1. We also found that the diurnal temperature range is decreased, right? The difference between maximum and minimum temperature is decreasing. We also look at the evaporation and the corresponding convective precipitation, right? But we have seen that due to this reservoir now, that area is receiving nearly 15% more precipitation within the vicinity of 10 kilometers. And that is mainly happening with fall when the lake is active, right? When the evaporation is happening. And on top of that, the wind speed is increased by nearly 50 to 60%, especially in the fall season when the wind, when the strong water is happening and the lake is evaporating. So why these findings are important? That's the key question. Looking at this climate and community interaction session, key findings are related to some of the interviews that were conducted in literature for the Saeed Nation. When the reservoir was created, there were some interviews, which is what we call traditional knowledge. And what we did is we cross-validated Western science research with the traditional knowledge. Trying to investigate, okay, what we have found, is it what people observed there during that time, or they are still observing it? So, but we have seen that, yes, people mentioned that once the reservoir started working, flying was done, that was like the interviews are showing that it's more windier now because of the reservoir, and that's what we have found, the wind speed is increased. Addition that it's more and cold. We also found that it's more humid, but we didn't find that it's cold. we found, on the contrary, we found that because of the reservoir, the temperature is increasing, right? Or it's being increased there. And that is because we have this whole thermodynamics happening, or convection is happening, the standard temperature range is changing. So anyways, we try to validate our Western science results with the traditional results, try to investigate how our Western science results are different than the tradition. This work is going to be submitted soon to peer review journal. As I mentioned, this work is mainly focusing on the reanalysis product and and observation. Another study, which is published in Climate Change Journal, that is where we did the same kind of work, but we used the WRF model, and where we created some scenarios, and in that scenarios we remove of reservoir, we replace it with the forest, making a kind of pre-net conditions, and then we try to contrast. Look, comparing my results with this one, we found that the results are kind of similar, but exactly the same because this is the artificial scenario-based work. But we also found that these are the results from the whole study are wrong. In this study, we did three different things. We compared the Western science with traditional knowledge. We look at the climatic impact of the reservoir, and we also try to look at the performance of the ARA 5 to simulate these kind of features. Because in the analysis product, there is no pre and post kind of features. Okay, I will stop here and any questions. Thank you.
So we have 2 minutes for questions, and in the meantime, I will.
I think there are no questions. I can leave.
Is there any questions?
Okay, thank you.
Thank you.
Yeah.
Yeah, it's okay. So you can use the computer here to change your slides. Okay, so our next speaker is Saeed Naeini. And so I'll let you start. You can stay. Can you?
Yeah. So, I'm Saeed. I'm a PhD student in Ecological Technologies of Thériault. I'm going to talk about the work we have done in our group called the novel deep reinforcement learning approach for optimizing coastal flood risk mitigation under climate change under superficial factors. So, tropical cyclones account for a massive amount of human deaths and injuries and considering the impact of climate change and a very increasing coastal population. The coastal regions of Canada have always been prone to such hazards. Specifically, Atlantic Canada faces higher risk from more acute flooding due to its geographic exposure, so the region will have more damage over next years. As an example, we can bring Hurricane Fiona happened in 2022 with maximum exceeding 100 kilometers per hour with large waves flooding in Atlantic Canada and Eastern Quebec. It was the costliest and most intense tropical cyclone that ever hit Canada, and as total economic damage was almost $660 million. So, if we want to reduce the risk of flooding over the communities, we have several approaches. Those traditional coastal protection design methodologies rely on historical data and they do not consider the future climate scenarios. So we're looking for adaptive, long-term, and cost-effective protection strategies supported by intelligent decision-making tools. So our goal is to reduce the current and future flood risk, not just considering the current climate, but also the future climate with considering the real world constraints like budget limits, for example, and that has to be based on data techniques. So if we consider there is a large coastal domain like this, and we want to find the best mitigation strategy, like seawalls barriers, and we have some constraints like budget limitation. So we basically work with the optimization techniques. We find out where to put those, like the strategies, for example, how much the height of the wall would be, and we do it with the optimization techniques. But considering that the problem that we are solving is over a large engineering system, and they are multiple states, for example, we want to reduce the flooded area or the volume of flooding, and we have also multiple actions, like for example, we are working with booms, barriers, and seawalls. So there's going to be several challenges. So what we propose a deep reinforcement learning. Deep reinforcement learning has three objects inside of it, like the agent that will go through the environment and find out and discover based off so you give an action to an agent, it go and explore through the environment to find the best mitigation strategy over there. And based on its performance, it will get a reward or it can cost. Like for example, if that is the strategy is fine, so we give it a reward. If not, we'll penalize. But it has some limitations still, so it has some pros and cons. For example, it learns from interaction and improves over time, and it excels in structured sequential decision problems, but it has some cons. Like for example, it struggles with sampling efficiency and may get stuck in local optima. So what we are proposing right now is this model actually. It's a combination of genetic algorithm with deep Q network, which is one kind of reinforcement learning. So we are basically getting the efficiency of genetic algorithm, we combine them with the DQN, which is the type of deep reinforcement learning. Then we find out some actions from the genetic algorithm, like efficiently, then we give it to the DQN. DQN would go through the environment and simulate the flooding. It would get its reward or penalized, and it will give the state, and then these rewards and states would go through both models. So both models are trained simultaneously. As a case study, we go with Magdalen Islands in Quebec. It's very low-lying, and is often and the critical infrastructure is often built close to the shoreline. And considering the climate change and sea level rise, those areas are expected to have increasing flooding. So the first step here is hazard model, which is flooding. So we have our climate. We want to work on current climate and the future climate. So we divide it into three climate scenarios: current climate, near future, and far future. Then we use the physics-based hurricane track model to simulate 10,000 years of tropical cyclones for each scenario. We gave them into the flooding model, which is a bathtub and very simple model to get the hazard maps. For more information on the work, you're welcome for my presentation tomorrow in 11:45 in Gallery C. So basically, these are the tracks we modeled we put them into the bathtub model to get the flooding, and these are some samples for visualization. So the goal is to minimize flooded area. It can be flood volume, for example, while respecting realistic constraints like the budget that we are having in the changing climate. And the action that we consider here is just seawalls, but you can put so many actions inside of it. So the framework supports combinations of actions, like you can have barriers, seawalls, all of them together, or even nature-based solutions. So we divided the region into 10 sub-regions, and the wall heights can vary depending on the climate scenario. We use a simple budget, like 55 units I wrote there, but it's kind of just a simple case. We wanted to try it out, so it can be like whatever dollars. And the cost per height, for example, for some regions from 1 to 4, we put some units for the cost per meter height. And for each scenario, we prescribe the possible wall heights for current from 0 to 1, near future 0 to 2, and for far future 0 to 3, in increments of 25 centimeters. So we designed the reward function, so if the cost exceeds the budget, it would penalize the budget to learn more from it. If the cost is lower or equal to the budget, so it has another reward function for that to minimize the flooding, simultaneously encourage the cost-effective solution within the budget. So we got these heights for the static one. The static is when each scenario gets its own best solution and not influenced by earlier ones. Like for example, in the historical one, if you have wall heights like 1 meter and you want to go for far future, for near future, and the model will tell you that, for example, for region 1, we don't need any walls, so you don't want to break them up. So we do it for each stage, for each scenario. It's like a static, and we do it for each scenario for themselves. So we got these heights for historical one, for near future, and for far future, and we got these results. These are without the walls, and these are with the walls. But as I told you, the static one is not the best one because it always gets best solution for each climate scenario and ignores the reality of continuity. For example, rebuilding costs or adapting existing structure. So we go with the adaptive one, which is more realistic, so you can build the walls upon the walls that you built before. So we got these wall heights for historical, near future, and far future. And these are the simulation results. These are without the wall, and these are with the wall for each scenario. And as a comparison, we see that for the static one, and here is the adaptive one. We saw that even for the adaptive, we could decrease the flooded area more. So an AI-based adaptive flood protection optimization technique was developed, combining GA, genetic algorithms, and deep reinforcement learning. The model was used to find optimal seawall configurations that minimize flooded area by respecting the budget limitations. The approach accounts for current and future climate scenarios, enabling adaptive strategies rather than static solutions. So the reward function balances flood risk reduction and construction costs, and integrating GA with DRL improves search efficiency and decision quality by leveraging the strengths of both methods. So the acknowledgement, and thank you.
Questions?
Yeah. Very interesting. Unless mistaken, you don't have a ground truth for your training model. So how confident are you that you are currently optimizing a flooding and not the model by itself, which you're learning algorithm?
So you mean the ground truth for the flooding model, like for example, simulating the flooding with walls or without walls? Without walls?
No, with walls. You
Yeah.
cannot train the model by training it on the truth, since you don't have walls and things that we could train on the past, like we do on the climate, for example. So now you're assessing, you're training it to see how good it is, but you're training and verifying and optimizing on the model.
Yeah.
So how sure are you that this relates with reality?
Yeah, if the flooding model works well with it, so if you have ground truth for your flooding model without wall, and you checked out with whatever, like for example with the real data, if you check out, for example, you're simulating the flooding, you check out your flooding simulations with the real data. If it works, so your model is working well. And then for that one, yeah, we don't have any data to compare, for example, with the wall. But for example, you can use those numerical simulation techniques to simulate the flooding with the walls. Like you can put the walls into for the geometry that you're simulating the flooding on, and then you get the results. If they are giving you results that they found. But yeah, I mean that's very important thing we have to consider. Thank you.
Thank you.
Thank you.
Yeah, I can.
Okay, thank you. So our next speaker is Nicholas Goodrow from University of Colorado. I just found that there's the affiliation on the application, but I don't have it here. So you can take the floor.
Okay, awesome. Thank you. Hi, my name is Nick. I'm from the University of Colorado Boulder. My talk is analyzing the effects of restrictions and incentive programs for outdoor residential water usage. I'd like to acknowledge my co-authors, Professor Aditi Bhaskar at University of Colorado Boulder and Professor Tanya Heikkila at University of Colorado Denver. So I generally look at water waste, especially in watering lawns, and this picture is a great example of that. It's one of the hottest days in Denver last year, and at about 2 p.m., the whole park in downtown Denver was watering their lawns. I thought it was a great representation of kind of my work. And so while most of my work is focused in the American Southwest, water usage restrictions are implemented in cities trying to achieve emergency reduction and just summer usage reduction, and that happens in Canada as well. So last summer, Calgary had the critical water main repair that affected water usage, putting in mandatory restrictions for large portions of the summer. And also the city of Vancouver estimates about 50% surge in water usage over the summer, and they have water use restrictions put in place generally. Water demand in Canada's driest cities remains highly seasonal, despite seeing per capita demand reductions over the past 2 decades. So generally water usage is going down, but there's still a large surge in water usage over the summers compared to the base usage. This is especially true in semi-arid and drier cities where that usage can almost double the winter usage. And water usage restrictions aren't just common in Canada or the US, they're all over the world. There's water rationing, which has happened in India, just conservation efforts like in Turkey, voluntary and enforced conservation in London, and Sydney, which is kind of a leading factor on this, is implement voluntary use targets and mandatory water usage restrictions during drought periods. The last one on here is San Diego. They implement water use restrictions since 2012. It's kind of in the area that I look at. I don't look at San Diego specifically, but I'm zooming right back into the Colorado River Basin, which provides water for about 40 million people for municipal usage. Many major cities are within that and within the diversions that are fed by the basin. So Los Angeles, Phoenix, Albuquerque, Salt Lake City, Denver are all using Colorado River Basin water. Some cities use about 60% of all their total water just for residential outdoor water usage, so watering lawns, filling pools, things like that. And the EPA estimates that an average American family uses about 100 gallons of water per day. For outdoor usage, that's much more, as you'll see later, in this region just because of the heat and the dryness. But along with the restrictions, many cities are investing in ensuring their water supplies. So Las Vegas installed a third intake valve in Lake Mead for the past couple of years, which cost almost $1 billion to ensure that consistent supply for residents. And in many cities, as you can see here, the red cities have implemented turf grass replacement programs. So offering residents money to remove their lawns and put in maybe xeriscaping, water-wise landscaping, or native grasses. For my work, we compiled over 30 cities within the Colorado River Basin, and we selected 7 for analysis. And so the amount of cities that we compiled was about 40% of residents within the service area. And we selected 7 cities, so that those being Los Angeles and Riverside in Southern California, Boulder and Denver in the front range of Colorado, Las Vegas in Southern Nevada, and Phoenix and Mesa right in the heart of Arizona. We chose these because they're generally some of the larger cities within the basin, but also are geographically spread out between many areas, and there's a ton of data available for all of them. So this area, unlike Canada, has issues with estimating the outdoor usage because during the summer, most of the time, water is being used all year round instead of maybe in colder climates when there's no watering outdoors in the winter. So traditionally, to estimate outdoor usage, you would kind of use this minimum month method where you find the lowest month of the year, say, oh, that's all indoor usage. But somewhere like Phoenix, where they're watering their lawn all year, that's not really true. So we partnered with a data company called Flume Data, which is a smart meter that you kind of put on your water meter, and it tracks the vibrations and uses AI machine learning to determine what your end uses of water are. So they gave us indoor and outdoor usage percentages for Los Angeles, Phoenix, Riverside, and Las Vegas. The other cities that we used, Mesa Falls is close enough to Phoenix to use that, but then Boulder and Denver, there's enough snow in the winter that we can assume the minimum month method holds up. So this is kind of what those percentages look like. These are just 3 of them. So you can see about 28% of all water in the winter in Riverside is used outdoors, while that being about 18% in Los Angeles. So this is kind of a time series of the water usage over time. You can see Boulder and Denver, like I said, we didn't need additional estimates, so they kind of zero out on their outdoor usage. Las Vegas, Boulder, Riverside, and Phoenix saw kind of general reductions in the peaks of water usage, but they were large amounts of water over time. As you can see, Las Vegas hitting close to 150 gallons per person per day used in summer months. And then all cities except Denver, Los Angeles, and Riverside saw a general decrease in water. Those ones were about even over our time period. So what we've done with all that data is model the effects of different variables and how they're affecting the outdoor residential usage. So what we've done is we've kind of compiled past studies and looked at things that they've done. So we use climate data to look at the mean monthly temperature, the maximum monthly temperature, the monthly precipitation, and the percent of days over 2.54 millimeters of precipitation. And we've also looked at historic water pricing structures. So 2 benchmarks for that, the first being 1,500 cubic feet of water, and then also we just estimated the average household cost of water. In our final model, as you'll see later, only these two variables were selected as kind of predictors of water usage, so monthly maximum temperature as seen on top, and then average cost of water as you can see on the bottom. But we also looked at how different policies put in place can reduce water usage, which is maybe a bit of a unique add to the rest of this previous work. So we adapted Catherine Harrison, who's a political science professor at UBC, her talking with the donkey approach, which groups different policies into kind of general ideas. And so things like the donkey part is like a stick to get it to move instead of putting a carrot in front of your head. So the 4 types that we identified were mandatory restrictions, which were restrictions that there were clear policies and enforcement. So something like the Calgary restrictions last year where there was very large economic fines for the amount of water if you're caught using water outside. Then voluntary restrictions, those were more like Vancouver's, where they're just asking people, maybe putting in guidelines or really small fines if you're caught using too much water. Strategic reduction, those are those turf grass replacement programs. Those can include the turf grass, but also maybe things like smart sprinkling or putting in smart sensors for your water usage. And the last one is awareness. So education programs, looking for policies or events where maybe a city put up a table at a farmer's market or has a little scholarship for school teachers to teach about water reduction. So the policies vary very greatly between each city. The voluntary restrictions were implemented in most cities, but really very noticeably not in Arizona. And so I think there is like maybe 2% a month, 5% a month in Mesa that had a voluntary restriction put in place. Phoenix never did. On the flip side, a city like Los Angeles Riverside spent probably most of their year under a voluntary restriction. Mandatory restrictions, even more so, you see that stratified. So Southern California, like I said, Los Angeles and Riverside see mandatory restrictions year round. There's fines if you're caught watering your lawn or different areas like that, versus cities in Arizona, which on their websites even state they're never going to have mandatory restrictions put in place. The strategic reduction policies were interesting. They were found in kind of the more suburban cities, which are Mesa, Riverside, and Boulder, compared to their maybe urban or more notable counterparts in Phoenix, Los Angeles, and Denver. And then the last thing, the awareness or education programs. Arizona cities were the only ones to really invest heavily in them. They're, as you can see in this time chart, they're beating all the other cities by quite a large margin. They all, every Arizona utility buys into a program called Water Use It Wisely, which educates the public on water usage. And so we took all of those and ran a bunch of different simulations and 432 different combinations of the policies, the climate, the cost variables, as I spoke about earlier. And the final selection was all four of the policy variables were there, along with the monthly maximum temperature and the average cost. We use a city fixed effects model to account for other effects that cities might have, maybe in land use planning or things that aren't trackable over time, density, age of residents, things like that. And interestingly to us, that no precipitation variable was found in the final model is likely due to the prevalence of maybe automatic sprinklers or things just on a timer where it's a set and forget setting instead of reducing your water usage or choosing when to sprinkle due to the amount of rain recently. So we used a city fixed effects model. This is all of our coefficients. It was used to account for factors, like I said, and policies that may not pertain specifically to water usage or things that may not be attainable. So some factors are maybe population density, the demographics, the housing age within the cities, HOA requirements or HOA prevalence in cities, and land use planning and zoning regulations. But notably, we did find that mandatory restrictions had the largest reduction potential. This was expected, but we've always been quite cautious about recommending mandatory restrictions due to them being maybe not socially or politically popular or sustainable long term. Voluntary restrictions, surprisingly to us, found a greater reduction potential rather than the strategic reduction. We think this is maybe due to some of the design of strategic reduction or turf buyback programs, which maybe aren't advertised as well as they could be. They're quite new policy lever that's being used by cities. Awareness was not found to be effective really at all. And finally, the last thing which is interesting that we found was average cost was found associated with higher usage. This is likely due to the monthly variations in cost versus maybe yearly changes in costs over time. So some of our conclusions, outdoor water usage generally has been decreasing in these urban areas. Many utilities have implemented these strategies to reduce their outdoor usage. Mandatory restrictions have found the greatest reduction potential. However, there's many questions about the sustainability of these programs. Voluntary restrictions can provide a soft alternative for mandatory restrictions, allowing for greater social and political flexibility for cities and utilities putting these in place. And strategic awareness programs can also provide substantial reduction. However, like I said, the design of these may still need to be optimized to reach their highest potential. And some of our future work is we're examining, as these turf buyback programs are in place, the urban heat and water quality effects that different landscapes have within cities, and then We just had a grant funded examining the effects of different water pricing schemes that have like overall and outdoor water usage, so we can kind of look at a different scale of the water usage, since the water going up, price going up isn't quite a sustainable or great conclusion to have. I'd like to acknowledge all of our data providers, all of the utilities that we worked with, Flume Data, our undergraduate students who helped me compile all of this, and then the National Science Foundation grants. Thank you.
We have time for question. Set up the last.
Regarding your model, did you apply the cross-validation for that? Is it a multi-linear regression model?
Yeah, it is.
So, how you selected the variables, right? Because different variables will have different weightages. Some will increase the R-square value, some will increase the noise in the model.
Yeah, we centered all of the variables before going, so we can easily track compared to each other. That was generally our idea for using that. I don't know if that answers your question.
So all the variables, like all the data you have, just put it into the model.
Yeah.
And we can look at like which variable has more weightage or which variable is reducing the efficiency or R-square value is going down.
No, not yet. Yeah.
Thank you.
Thank you.
So the last speaker of the session is Melissa McDonald from Environment Climate Change Canada.
There's a bit of a lag.
And it is a virtual presentation.
Yeah.
So the last speaker of the session is
How about now? Okay, I found it. Sorry, everyone. I see that it's showing me that my volume is working, so I assume everyone can hear me. All right. So yes, I'm Melissa McDonald with our Health and Air Quality Forecast Services Program with the Meteorological Service of Canada, Environment and Climate Change Canada. And I'm here today to talk about a new metric that has been developed in collaboration with a colleague of mine at Health Canada. To look at how we can estimate population-based wildfire smoke exposure. So just want to start off with acknowledgements to my colleague Carlin Matz with Health Canada, because this was her idea and she was supposed to be here to present today, but difficulties with funding came up and I'm here today instead. I'd also like to acknowledge my Environment Climate Change Canada colleagues, Celine Ardette, my manager, as well as Morgan Mitchell, an air quality scientist working in the Atlantic region, as well as my Health and Air Quality Forecast Services co-op and student team that have been supporting the calculation of this metric. So just a little bit about wildfire activity in Canada to get started. Approximately 7 million wildfires occur each year in Canada, on average burning 2.7 million hectares a year. 50% of these are caused by lightning strikes, usually in remote areas, and they account for 85% of the area burned. 2023 was an unprecedented year, and so in that case, we are going to use that as our example for this metric. Most of the wildfire activity occurs in BC or along the boreal forest areas through the territories, northern prairies into Ontario and Quebec, which leads to wildfire smoke. So smoke from wildfire causes high exposure to pollutants, in particular particulate matter, which is the main way that we look at wildfire smoke. It's present in areas around the fires, of course, but also can expand to thousands of kilometers away through transport. So this image is from the 2018 wildfires in BC, and you can see the smoke really quite heavy and thick right across Saskatchewan, and even further east than that. These wildfires are the leading contributor to population-weighted PM 2.5 exposure. So that's particulate matter of 2.5 microns or smaller. And that exposure in Canada accounts for 17% of the exposures. A little bit about wildfire smoke and health. It's the major source of air pollution in Canada, and it's only expected to increase with climate change. Epidemiological studies have investigated the health effects of wildfire PM 2.5, and they do that by comparing the rates of outcomes between fire and non-fire periods, the health outcomes. So we have found that wildfire PM 2.5 associated with wildfires is strongly associated with adverse respiratory effects and premature death. There's also some evidence of an association with cardiovascular effects and reproductive and developmental effects. But there needs to be more research done, as there's only limited evidence associated with mental health effects. And I've seen other pieces that have alluded to there being more mental health effects than has been found in the research. Some of the groups that can be really disproportionately impacted as compared to others by wildfires. The major at-risk groups under air quality events, such as young children, women, seniors, and people with pre-existing respiratory diseases, but also definitely disproportionately impacting other groups, such as pregnant people, populations with lower socioeconomic status, Indigenous populations, people living in remote areas where a lot of these fires occur, and also those that are engaged in strenuous outdoor work during these events, such as wildland firefighters. So just a little bit about how we forecast and measure AQHI, or air quality. We do that through something called the Air Quality Health Index. The Air Quality Health Index is a scale using numbers 1 through 10 or 10 plus, and it's calculated using a rolling average of 3 very common pollutants, air quality pollutants in Canada, the ozone, NO2, and PM 2.5. And the scale can be used as a self-calibration tool. So we consider an AQHI of 1 to 3 to be a low risk to health, 4 to 6 to be a moderate risk, 7 to 10 to be a high risk, and 10 plus to be an extreme risk. So the population can self-calibrate using the forecast to find out what values impact them. Those that are more at risk may find that lower values are when they have to take action and protect themselves against air quality. But as I mentioned, it's a 3 pollutant index. And we know that when it comes to wildfire smoke, PM 2.5 is the major pollutant that is causing the impact. So there's been work and studies done to associate an AQHI with a single pollutant value for just PM 2.5. We call this AQHI plus PM 2.5. So it's how can we look at a single pollutant and for extreme events to protect human health. This has been developed based on research from the BC CDC and Yao, who was part of that work research. And the AQHI plus for PM 2.5 can be calculated by taking the concentration, so the PM 2.5 concentration, dividing by 10, and then taking the ceiling value or rounding up. And what we do when we present the observed AQHI to the public is that we actually calculate the AQHI plus PM 2.5 as well as the regular 3 pollutant AQHI. And then we take the maximum value is what is reported between the two. And those can be found on WeatherCan app as well as on our weather website. So this leads to development of the actual metric. So the population-based wildfire smoke metric. Through a lot of Carlin's research, she was trying to look at exposure to wildfire smoke. And it became very apparent that it's difficult to do that real time or with the event to actually consider those that may be impacted by the wildfire smoke. We definitely see increases in healthcare utilization due to wildfire smoke, but it's always identified after the event. And it's difficult to achieve those values very quickly without months of analysis following the events. So we thought of person days, and that's the idea of combining the air quality metrics. In this case, we're looking at the number of days of air quality alerts with population accounts. And so we can take a given period, let's say a week, a month, a year, and look at the number of calendar days is how we're looking at it, the number of days impacted by wildfire smoke, and then multiplying that by the size of the population that's impacted. And this can give us a value that will quantify the number of people that are at risk for the adverse health effects due to wildfire smoke in that period. So we'll bring it back a little bit full circle here to why I talked about AQHI. So we defined a smoke impacted day as a day when there was an air quality alert in effect. We have 2 different types of air quality alerts, a special air quality statement, which is issued when an AQHI is expected to be 7 or greater, which was at their high impact level or high risk level, or an air quality warning, which we referred to as an air quality advisory last year, when the AQHI is expected to be a 10 plus, which was their extreme risk level. And ideally, we would do this for only wildfire smoke events. However, our alerts are not captured that way. We issue our alerts for all different types of air quality events. So when looking at the data that I'm going to go over with you from 2023, please note that there is the chance that we are counting a couple of days of when there was an ozone or smog event, but those are very few. The majority of all air quality alerts across the summer in Canada are all related to wildfire smoke. And where our ozone or smog events do occur are in usually our urban population centers. And if I recall from 2023, there was a few of them. I would say like maybe 2 days across the whole summer. The forecasters don't only consider the observed AQHI when they do issue an air quality alert. They're working with models that show the expected PM 2.5 coverage. They use satellite information, and we do have some other ways of looking at some observations of PM 2.5. So this graph here on the left is looking at for the entire 2023 wildfire season from May to October. It's the number of millions of person days that we calculated. So we did reach a grand total in 2023 of nearly 650 million person days. We divided the country here by different regions, looking at the BC, the prairies, central Canada, Ontario, and Quebec. Atlantic Canada and the north, so the territories. And then we're looking in each of the columns at the different months throughout that period. So May through October, and then also the total for the entire season by each of those regions. This orange line across the graph is the total for Canada for each of those months and then for the entire season. You do see some significant numbers pop up. So for example, in June 2023, this is when a lot of the smoke and wildfire activity from out west was reaching the more urban areas or the Greater Toronto area, as well as southern Quebec. We can also see ever so slightly just this little tad of purple sticking up in June. I happen to be located in the Halifax area, and we had wildfire right on the outskirts of the city in June 2023, which is extremely rare to have even seen Atlantic Canada be able to pop up in terms of population with other areas. And you also see here in August where the blue prairie regions highlighting quite a bit higher, and this is when they see a lot of their air quality alert activity. So this map here is just days. I'll just start with that. This is kind of where Carlin sort of came up with the idea. I was creating these maps regularly, annually, now monthly, to sort of look at the number of days an air quality alert was in effect across the country. So each of these rectangles or dots in the north are actual forecast regions, or regions where we would issue an area forecast, or in this case, alerts. So in each square, I'm counting the number of days throughout the entire wildfire season of 2023 when there would have been an air quality alert in effect. I like to highlight up here on the black underneath these gray dots right across the map show the area burned for 2023. But up here in northern Alberta, some of southern Northwest Territories, we reached over 125 days under an air quality alert for the wildfire season of 2023, out of only a potential about 150 days, I must add. So it was a significant wildfire season for the Northern Prairies and Southern Northwest Territories in terms of the number of alerts that were happening, and in very low populated areas, I should add. And then also you can see here in Northern Quebec where we've seen some much more than usual wildfire activity, where we were reaching up to almost 75, 85 days under air quality alerts in this area as well. But it didn't really necessarily represent the population at risk. In this case, we were only thinking of just how many days. And it wasn't really necessarily significant as the number of people, because this was also the same year where we started hearing a lot of chatter and requests and concerns around air quality from southern Ontario and southern Quebec. And as you can see here, you're not really seeing those numbers represented in this map. So fast forward to calculating air quality person days. And this, instead of the millions like before, this is counting the number of hundreds of person days right across the map in each of our forecast regions. So as you can see, things become very bland and blue for the majority of country when we're talking about person days alone. But I'd like to just highlight up here again in the northern Alberta area where we're seeing still this like dark yellow color that would represent 30,000 person days in this year. So that's upwards of 3 million person days for the season. You also see over here where you start to see like the southern Ontario and the southern Quebec area really start to pick up in numbers. I'm going to zoom into those closer here with a few individual maps. On the left-hand side, we have the number of days. On the right-hand side, we have the number of person days in hundreds. So just highlighting here that for the Calgary area, this little square here, or area here, we were only looking at around maybe 25 to 30 days of air quality alerts. But when you take into account person days, that means that there was 30 million days, or 30 million person days where the population was at risk to the adverse effects of air quality. In the Edmonton area, we went from around 40 days, let's say, up to over 50 million person days. And then southern BC definitely shows out significantly with Vancouver as well here in the darker color. And then on to my last slide. First, just to talk about Saskatchewan, where we see Saskatoon pop up here. And we can see that Saskatoon had over 10 million person days of potential impact in the 2023 season, as compared to about, let's say, 40 days under air quality alerts. Winnipeg was similar too, even showing higher person days. But I think the most significant images sit when you look at the highest populated areas. Montreal here, where we see over 50 million possible person days. And then here in Southern Ontario, when we see a potential of over 30 million person days from only 10 days of air quality alerts. And that's really what brought on those media inquiries and interest from the Southern Ontario and Quebec during these events. So overall, just in conclusion, it was just an interesting metric, or a better way for us to be able to look at air quality, or the potential impacts of air quality. And that's everything. I know it's really hard to answer questions this way. I don't know if it's possible. And that's everything. I know it's really hard to answer questions this way. I don't know if it's possible.
So unfortunately, we don't have time for questions, but I encourage you to contact us directly.